Hello, medical research pioneers, to a crucial exploration in our machine learning journey. I'm delighted to guide you through this episode, where we'll tackle a classification task using a significant dataset and a powerful explainability tool. I'm working in Google Colab, breaking down the process into clear steps so you can follow along as we classify breast cancer diagnoses. Let's kick things off by setting up our environment and assembling our tools for this impactful health study. I start by installing the interpret library in Colab with a simple pip command. This library will enable us to dive deep into explainable AI, helping us understand our model's decisions. Next, I import the necessary tools. NumPy for numerical operations, Pandas for data manipulation, and Sklearn's load breast cancer function to access our dataset. From Sklearn, I also bring in train test split to split our data, random forest classifier for our model, and accuracy score and classification report to evaluate performance. From interpret, I import partial dependence from the black box module, our tool for global explanations, along with the show function to display results. I also import matplotlib's pyplot for potential visualizations, though we'll focus on interpret's built-in plots. I set a random seed with NumPy's random seed set to 42 for reproducibility. With our toolkit assembled, let's load the data. I'll load the breast cancer Wisconsin dataset using Sklearn's load breast cancer function. I create a data frame with the feature names provided by the dataset, 30 features like mean radius, mean texture, worst perimeter, and more, and add the target column, where 0 means malignant and 1 means benign. I print the first few rows to examine the data. The first row shows mean radius 17.99, mean texture 10.38, mean area 1001.0, worst area 19.0, and target 0, indicating a malignant tumor. The next row has mean radius 20.57, mean area 1326.0, and target 0, also malignant. This dataset includes 569 samples of breast cancer tumors, with 30 features derived from digitized images of fine needle aspirates, measuring characteristics like radius, texture, and smoothness. The target is binary, 0 for malignant, 1 for benign, with 212 malignant and 357 benign cases, making it a binary classification task. Let's prepare the data for modeling. I split the dataset into features, and target X includes all columns except the target, the 30 features, and Y is the target, 0 or 1 for malignant or benign. I use train test split to allocate 20% for testing and 80% for training, with random state 42, giving us 455 training samples and 114 test samples, approximately 43 malignant and 71 benign in the test set, based on the dataset's 37 to 63 split. The features are all numeric, representing tumor measurements, and there are no missing values, so we're ready to train our model. I initialize a random forest classifier from Sklearn with 100 estimators and random state 42. Random forest classification is an ensemble method that constructs multiple decision trees, 100 in our case, each trained on a random subset of the data and features. It aggregates their predictions through majority voting to classify outcomes, reducing overfitting and improving accuracy, making it perfect for classification tasks like diagnosing breast cancer, where features may have complex, nonlinear relationships with the target. I call fit on xtrain and ytrain to train the model, allowing it to learn how features like mean radius and worst concave points distinguish malignant from benign tumors. Once trained, I make predictions on xtest with predict, storing them in ypred, and evaluate with accuracy score and classification report. The results are impressive. Accuracy score 0.9649 to 96.49% correct predictions, or 110 out of 114 samples. The classification report details: for malignant, precision 0.98, recall 0.93, F1, score 0.95, support 43. For benign, precision 0.96, recall 0.99, F1, score 0.97, support 71. Macro average F1 score is 0.96, weighted average 0.96. Strong performance across both classes, with a slight edge in detecting benign cases. I use partial dependence from Interpret's black box module to explain our model's behavior globally. Partial dependence is an explainability tool that shows the marginal effect of a feature on the predicted outcome, averaging out the effects of all other features. In classification, it examines the predicted probabilities, helping us understand how a feature like mean radius impacts the likelihood of predicting benign, class 1, across its range, revealing trends and relationships. I initialize partial dependence with our model's predictproba function to get probability outputs, xtrain as the background data, and the feature names from xcolumns. I generate a global explanation with explain global and visualize it with show. On screen, you're seeing the partial dependence plot for mean radius, one of the 30 features analyzed. The title reads name, mean radius type, continuous hashtag unique, 381, indicating mean radius has 381 unique values in the training set. The x-axis shows mean radius values from 7.6 to 28.1, with specific points like 7.6 to 9.15, 9.15 to 10.6, up to 25.2 to 26.7, and 26.7 to 28.1. The y-axis shows the average response, the predicted probability of class 1, benign, from 0 to 1. The plot has a blue line with a shaded confidence interval, showing how the probability changes with mean radius. At mean radius 7.6, the probability is around 0.9 to 90% chance of benign. As mean radius increases to 10.0, the probability remains high, near 0.85. Between 10.0 and 12.1, there's a gradual decline to about 0.75. From 12.1 to 15.0, the probability drops more noticeably to around 0.5 to 50% chance of benign, indicating a transition point. Beyond 15.0, the probability continues to decrease, reaching about 0.3 at mean radius 20.0, and stabilizes around 0.2 to 20% chance of benign, from mean radius 22.3 to 28.1. This trend shows that larger mean radius values are strongly associated with malignant tumors, as the probability of benign decreases significantly. Below the plot, an orange histogram shows the distribution of mean radius values, with most data concentrated between 10.0 and 15.0, fewer samples at the extremes like 7.6 or 28.1, which explains the wider confidence intervals at those ends. This plot highlights mean radius as a critical feature, with a clear negative relationship to the probability of a benign diagnosis. Let's reflect on these outputs. They're a diagnostic guide for our model. The first row showed a tumor with mean radius 17.99, mean area 1001.0, worst area 19.0, and target 0, malignant, while the next had mean radius 20.57, worst area 1956.0, and target 0, also malignant, suggesting larger tumors are often malignant. Accuracy of 0.9649 means 96.49% correct predictions, 110 out of 114 test samples. The classification report confirms malignant has precision 0.98, recall 0.93, F1, score 0.95 for 43 samples. Benign has precision 0.96, recall 0.99, F1, score 0.97 for 71 samples. Excellent performance, slightly better for benign cases. The partial dependence plot for mean radius showed a high probability of benign, 0.9, and mean radius 7.6, dropping to 0.5 at 15.0 and down to 0.2 at 28.1, aligning with the head's larger mean radius values, 17.99, 20.57, being malignant. The histogram confirmed most mean radius values are between 10.0 and 15.0, where the probability shifts significantly. Partial dependence's global view helps us understand how features like mean radius influence predictions across the dataset, making our random forest behavior interpretable. To conclude this health research journey, we've analyzed the breast cancer dataset, a 569 sample study of tumor characteristics, and trained a random forest classifier, achieving an accuracy of 0.9649 and a macro F1 score of 0.96. The global explanation via partial dependence revealed mean radius's strong negative impact on the probability of a benign diagnosis, providing a clear view into our model's trends. Random forest classification's ensemble approach captured complex tumor patterns, and partial dependence marginal effect analysis offered transparency for our black box model in this binary classification task. Grab this code, explore other features like worst area, and dive deeper into cancer diagnosis. I'm inspired by this medical analysis. Hope it sparked your curiosity about data's role in healthcare. See you next time for another meaningful data exploration.